In this Transform Training Series video, we will cover basic programming in Modelica by modeling a set of simple ODEs, or ordinary differential equations. This example will introduce the user to defining parameters and variables, initializing state variables, writing ODEs, specifying annotations, and controlling the length of the simulation. As always, the solutions presented in the video can be found in the Transform Training GitHub site. Let's start by creating a new package where we can save our work. Go to File, New Package. We'll call it Introduction to Modelica. Within the package, let's create a new model. Right-click, New Model. We'll call this one Lorenz System. Click OK. For this example, we'll be working just on the source code, so we'll go to Modelica text. We'll start a model by writing down the equations in an equation section. For this, we'll use the dir operator as shown there. The dir operator allows us to specify the derivative of the variable enclosed within the parentheses. We'll write each of the equations that were shown on the introductory slide. And with that, we've done everything we need in order to write our equations. The Modelica translation and solving process will take care of the rest. If we check our model, we'll get a bunch of errors because at this point, Modelica doesn't know what type of variables these are. Let's fix that. First, let's specify x, y, and z. X, y, and z are our variables which will change with time. So we'll give them the type real. And give them a description so we know what they are. Next, we'll define the parameters of the system, sigma, rho, and beta. With our parameters and our variables now specified, let's go ahead and check the model again. Upon checking for errors, apparently I misspelled one of my parameters. Let's go and fix that. And check again. And we now know that we have 3 equations and 3 unknowns. At this point, we should be able to simulate. Before looking at the results, let's look at the translation warning real quick. It is telling us that we have not given a fixed start value for any of our continuous states, x, y, and z. So it is assuming a start value of 0. That's okay. We'll come back and fix that later. Let's look at our results. Let's plot x, y, and z. Those are not very interesting results. Given our start values are all set at 0, that might be the reason why. Let's go ahead and correct that now. Go back to the modeling. At this point, we'll control the initial value of x, y, and z. For that, let's go ahead and define x, y, and z start. And we'll copy that down to speed things up a little bit, making sure to change our descriptions. Now that we've specified start values, we need to somehow link the start value here with the variable that we care about. To do that, we will use an initial equation block and say x equals x start, y equals y start, and z equals z start. With that, let's go ahead and simulate and look at our results. First off, we can notice that we no longer got any translation warning, indicating that our start values have now all been set. Now we can look at our results. The x, y, and z coordinates all now do things. Much more interesting than the 0 answer we had before. But let's increase the simulation length now by going to Simulation Setup and extending the stop time to, say, 100 seconds. And we'll increase the number of intervals to 1,000. Push OK and resimulate. These results don't mean much to us now, but think of these as x, y, z coordinates. If we were to transform these into 3D space, we would be able to produce the figure that was shown on the introductory slide. Another thing to point out here is the ability to do an investigation into how your parameters change the results of your model. For example, let's change sigma to 5. We'll click here, change it to the number 5, and resimulate. As you can see, that made a big difference on our results. Let's go ahead and change that back to 10 and resimulate them all. Another way to investigate parameters is to do a parameter sweep. Drag the variables that you'd like to change and the results you'd like to view. Specify the minimum value and the maximum and how many simulations you'd like to perform. Next, select X as the variable you'd like to plot. Then click Run Sweep. What was just performed was 10 simulations varying sigma from 1 to 10 and plotting the results of each of those for the variable X. Let's return our simulation back to what it was before. We'll go ahead and close the parameter sweep, close this plot, close all of our results, and resimulate, plotting the variable X, Y, and Z. There are two last things I'd like to cover. Let's go back to the Modeling tab and click Information. In the Information tab are the parameters associated with our model, along with the descriptions we specified. If we right-clicked our model and selected Parameters, we'll see these parameters once again with the descriptions. Given that the X start, Y start, and Z start values are part of our initialization, let's go ahead and assign them to their own group. For this, we'll go back to the modeling text and use annotations. After each of the X start, we will write the keyword annotation. Specify dialog. Use the keyword group. And we'll assign them to the initialization group. Let's go ahead and copy and paste this to each of these start values. If we go back to the Lorenz system and right-click and choose parameters, we'll see that we now have two groups, one for parameters and one for initialization parameters. Using annotations, you can control the way in which people can interact with your model. Another option is tabs. If we use tabs, instead of having a separate group, there'll be a new tab called Initialization, and the parameters will be specified there instead. Using groups and tabs, you can organize your information. This is very important as your model gets more complex and you have more and more parameters. Let's review what we've done in today's training. First, we coded 3 differential equations for the variables x, y, and z. Next, we defined parameters and variables for our system, including start values. We then set the start values of x, y, and z to the values we'd specified. Next, we specified annotations to control where our parameters show up on the parameter GUI. Finally, we altered our simulation settings and saw the impact it had on our results. If this is your first exposure to Modelica, I hope you start to realize how powerful this language can be. It allows you to create very complex systems very quickly. If you'd like to learn more about Modelica, please visit the Modelica Association website at modelica.org, or you can check out my other transform-related videos. Thank you for watching.